So guys, now going forward, I have enumerated here the route insertion algorithm. I request you to go through these 6 steps of route insertion algorithm and try to relate that we have actually exercised all these 6 steps in the examples so far we have discussed regarding route insertion in the M-trie data structure. Alright. Nevertheless, we will going to discuss one more example of route insertion in the M-tree. So far our M-trie data structure has taken the following shape as you can see on the screen. And now the next route that we will going to insert is the route number 5. Alright, so we will going to insert the route 128.128.0.0 and the mask value is 16. So obviously we will going to convert this route into its effective prefix form. So as you proceed towards inserting this route into this M-trie data structure, we start our traversal from the root node of this M-trie data structure. Alright, so the very first bit of this new route is 1. So it means that we will going to take the path along the 1th child of the root node of the tree. And we land at node number 3. And now we start comparing the effective prefix bits of the new route with the effective prefix bits of the current node in the M-trie. So you can see that the first 8 bits of this node number 3 matches with the first 8 bits of the new route, but the mismatch happens at the following bit, that is bit 0 in the node number 3 and the bit 1 in the new route. Alright, so the node split algorithm will be triggered again at node number 3 and the split will happen on this bit 0 which is highlighted in pink color. So once again the node split algorithm will be triggered at node number 3 and as per the algorithm we immediately create 2 new nodes, the daughter node as well as the niece node. So let's say this time the daughter node is the node number 7 and the niece node is the node number 8. As a part of the algorithm, all the children of the node which is undergoing a split is transferred to the daughter node. Alright, so it means that the node number 5 and node number 6, which are the children of node number 3, will be transferred to the node number 7. And as it is, it's just a plain copy paste. If you had more nodes which are the descendants of the node number 5, then those nodes would have also moved as it is, being the descendant of the node number 5. So in fact here we are transferring the entire subtree which is rooted at node number 5. So when I say moving the children, that is node number 5 and 6, it simply means I am moving the entire subtree which is rooted at node number 5 and the entire subtree which is rooted at node number 6 from the node number 3 to node number 7. Alright, so remember that we are just not moving the children, we are moving the entire subtree. Now the next thing that would happen is transferring the bits from the effective prefix of the node which is going under a split. So these many bits, that is starting from the mismatched bit up to the last bit, all the bits in the effective prefix of the node 3 will be transferred to the daughter node. Alright, so these 8 bits will be transferred to the daughter node and the parent node 3 will remain with the following bits which are left over. So it means that node number 3 would left with the following effective prefix. And the length of the effective prefix would be reduced from 16 to 8 because the remaining 8 bits has been transferred to the daughter node. The data of the node number 3 before split was null. Therefore, copy the data from the parent node to the daughter node data would also be null. And finally, copying the bits from the input route, starting from the mismatched bit up to the last bit, we will simply copy all these bits as the effective prefix bits of the niece node. Alright, and the niece node is made the 1th child of its parent because its first bit is 1. And the daughter node is made the 0th child of its parent node because its first bit is 0. So we have successfully executed the insertion of the route 5 in this empty data structure. Alright, so it is the node 3 which will undergo split again, and it will give birth to the new node 7 and node number 8 in the M trie. So if you want to see one complete tree, the following is the tree which would be created after insertion of 5 routes that we have discussed. So this is the final tree, and tree keep growing as more number of routes are added to the tree. Alright, so node merge happens and tree shrinks when the routes are deleted. So we will going to discuss route deletion algorithm in detail, and having understood the route insertion algorithm, the route deletion algorithm would be a cakewalk. The route deletion algorithm would be exactly opposite to the route insertion algorithm. So in this M trie data structure, which you can see on the screen, we have inserted these following 5 routes. And you can see that in this M trie data structure, we have 5 leaves. You will have as many leaves as many routes you have inserted in this M trie data structure. So node number 2 is leaf, node number 4 is leaf, node number 5 is leaf, node number 6 is leaf, and node number 8 is leaf. The path from the root node to the leaf node represent exactly one route. Alright. Next we will going to discuss the route search algorithm. Route search algorithm means that in this tree we know that we have already inserted 5 routes. What if I tell you that, hey, tell me whether the route 128.2.0.0/16 is present in this M trie or not? So you have to come up with the yes or no answer that whether the route is present or not. As simple as that. So that is called route search algorithm, and not to be confused, it is not a longest prefix match algorithm. Alright, I'm simply telling you that given a route, search whether this route was inserted in this M trie data structure or not. So that is the route search algorithm which we will going to discuss next. So guys, with this we have completed the route insertion algorithm, and as a part of exercise I would suggest you that you try to draw your own M trie data structure and see how does the M trie data structure transform when you insert the following routes in this already constructed M trie. Alright, and the time complexity of inserting a route in this M trie data structure is order of k, where k is the number of bits that you are inserting. So for IPv4 routes, k is a constant which is 32. So in other words, the time complexity of inserting a route in this M trie data structure is order of 1.